In this lesson, we're going to talk about objective 8.2 pH and pOH of strong acids and bases. So the objective states that we should calculate pH and pOH based on concentrations of all species in a solutions of a strong acid or strong base. So we had talked about a long time ago that molecules of strong acids will 100% dissociate in aqueous solutions to produce hydronium ions. All right, so remember, strong acids are strong electrolytes. Think of these strong electrolytes as there will be none of it left, okay? And so with our acids releasing our hydronium, whatever the concentration of your acid, HA, will be the concentration of hydronium, okay? And this is because, going based off my original video, if I have a strong acid in water, it will make a conjugate and hydronium. So here, if this is considered my limiting reactant, and this is 1 molar, then our conjugate will be 1 molar and our hydronium will be 1 molar because it 100% dissociates. Now listen, just because the HA was 1 molar means that all of it will be used up. So you won't have any HA remaining. Please note that I did have one single arrow. I don't have a double arrow. A double arrow indicates that you're going to have some reactants and some products remain in equilibrium. This is not at equilibrium. You're using up all of your acid. It will break up 100% into its ions, okay? Now we had talked about in 8.1 how to solve for a pH based off hydronium concentration. So we would take the negative log of the hydroniums. So this is kind of the best part. If you have a monatomic ion, so here 1 singular hydrogen, just take the negative log of the hydronium. If it is not monatomic and you have we can call it a diprotic, di meaning 2. So let's say it's H2SO4, like right here. You're going to have 2 hydronium ions for one of the H2SO4. So it's just something to be wary about. We had learned there are 6 strong acids, 3 of which are in group 17. Then we have perchloric acid, HClO4, sulfuric acid, H2SO4, and nitric acid, HNO3. You do need to memorize these. And if you come across an acid that is not one of the 6, it is automatically a weak acid. So some examples, HF. HF, although is in group 17, it is not considered strong, it's weak. Another example, acetic acid. Almost forgot how to write that. Here, not one of the 6, so it would be considered a weak. I should probably write this for him that comes back. Weak acids, because they're not one of the 6. There is a saying online. I don't know if it's going to help you to memorize these 6, but it's called "So I brought no clean clothes." Here it's supposed to help memorize the 6. The SO being for the sulfate, H2SO4. I for HI, BR, HBr, NO for the nitric, Cl for the ClO4. Actually, no, sorry, Cl, my bad. And then ClO for the perchloric, okay? Use it if you would like. Totally up to you. I think it kind of might leave some room for misinterpretation because a lot of students think that HClO3 is a strong acid. Okay, here that is not going to be part of this case. It will be just HClO4. Just be wary if you do look online. A lot of websites say there's 7 strong acids and they actually include this HClO3, but for the AP test, they just have you focus on these 6. So this is probably what you just need to stick with, okay? Let's go to the next page. So here, when dissolved in solutions, now let's talk about strong bases. Just like strong acids, they will 100% dissociate into its ions, one of them being the hydroxide ion. So here bases, our base concentration will equal the hydroxide concentration because we had learned our base will break up into the B positive, the cation, and hydroxide. All right. And so here, this is a limiting reactant. So here, if this is 1 molar, this will be 1 molar, this will be 1 molar. Again, this is because it 100% dissociates. Please note, I did also use one single arrow. I did not use a double arrow. And here, like we learned in 8.1, pOH is the negative log of hydroxide. Our strong bases are going to be group 1 or group 2 metals attached with hydroxide. Technically, not all of them should be associated with this. Like, for example, francium, you're really not going to see it. But here, the AP test is just going to use the strong ones. There is talk about magnesium hydroxide, like should not be listed as a strong base, but they still include it. So here, again, it'll be a group 1 or group 2 metal. So here, like sodium, great example, calcium, 2 positive. Again, all attached to a hydroxide, okay? Now, let's say you do come across something like this. Here, great, there's a hydroxide. Great, it's a metal, Fe, but Fe is not a group 1 or group 2 metal. That's supposed to be Fe. Why does it not look like that? Here, this would be considered a weak base. This is not part of this. Also, I do want to note that there are some bases that don't have hydroxides, and I'm not trying to confuse you too much. One other example is NH3, okay? We'll talk, the AP test likes to talk about NH3 all the time, but if you think about it, when we get to our weak stuff, you'll kind of understand that it doesn't technically need to have the hydroxide because it can have the water help it get a hydroxide, which again, we'll talk about in 8.3, okay? All right, so let's finally start doing some calculations, and I do have some examples for you to try as well. Now, my advice before we start these 2 examples, always write out the dissolving reaction first, okay? Also, change this to -3. Always write out the reaction first, then do the multimole ratios, okay? So we have HCl. So based off practicing how we write the actual reaction, the dissolving reaction, HCl reacts with water to make hydronium and Cl-. So here, this is 0.01, which means hydronium's 0.01, and so is the chloride. So here, calculating pH, I'm going to take the negative log of 0.01, which is coming from the hydronium. You get the pH as 2. All right. Now, one thing I do want to note, I know it kind of seems tedious to have to write the reaction, but I would encourage you to do so because if there's a situation where you need twice the amount of hydronium, you writing the reaction will remind you, okay? All right, so let's try this one. Calculate the pH of 1 × 10⁻³ molar NaOH. So here I have NaOH, and it's going to break up into sodium ions and hydroxide ions. So here, if this is 1 × 10⁻³, these are both 1 × 10⁻³. So right now, I have the hydroxide concentration, but the question is really asking for pH. We cannot use the pH equals negative log of hydronium just yet, okay? So what I'm going to do is there's actually 2 ways that we can go about this. We can use the KW equation where we know hydronium multiplied by hydroxide, or we can solve for pOH, negative log, to get the pOH to then use pH plus pOH equals 14. So this is one way, this is the other. After this one, then you can use pH. but there's technically two routes that you can take. I find the second way is the most preferred way because then you don't have to be using 1 times 10 to the negative 14, because if you've been struggling with exponents, it's probably best to stay away from that. So I'm going to go the second route. So let's take the negative log of 1 times 10 to the negative 3. Here you're going to get the pOH as 3. Then to get pH, I'm going to do 14 minus 3. I get my pH as 11. Now, both of these, part A and part B, make sense because since this is HCl, is a acid, my pH was less than 7 in an acidic solution. And then in part B, NaOH is a base, so it should have a pH greater than 7, which it did, okay? All right. I have actually have 3 example problems for you to try. Why don't you pause the video, try this out yourself, and then press play and I'll go over the answers. All right, let's go over these answers. So first one, calculate hydronium that has a solution that has a pH of 2.2. So here, I know this equation is not on your equation sheet, but we do still have to get this down. Here to get hydronium, we did do 10 to the power of negative pH. So here I did 10 to the power of negative 2.2. I got my hydronium as 0.0063 molarity. Now, if you're a student that's wondering, ooh, can I just leave my answer as 10 to the power of negative 2.2? This is not going to be an acceptable answer because you probably need to use this value of 0.0063 molarity for something else. Let's say it asks you further for grams or something or moles. You're not going to be able to work with 10 to the power of negative 2.2, okay? Part B, here, there was 2 ways to go about this problem because it wanted you to solve for pH and they gave you a hydroxide concentration. So here, I'm going to do the easier way of getting a pOH to then get pH, but you could have used hydroxide to get you hydronium to then get pH. That is another way as well. So here, pOH, I did the negative log. I got my pOH as 4. So then 14 minus 4 gave me my pH of 10. And then lastly, calculating the pOH of a solution that has this pH of 1.95. Very simple problem. We just do 14 minus 1.95 to get our pH as 12.05.